Let's see if we can get this going. You know, America is a strange country in many ways. And the one way in which I wanted to mention this is that you can drive along a country road and you see a vegetable stand, and the farmer is trying to sell vegetables and stuff, and they have this vegetable sitting out by the side of the road, and there's a little box there. It says, you know, put the money here, and just leave it there. It's you know, what we call the honor system. There's very few other countries where that would happen, where you could leave a box of money, or even ask people to just leave what is due, and not just take the stuff and not put anything in it. But America is kind of nice that way. On another, not quite related topic, it's probably the most generous country in the world too. That's besides the point. So we're going to do this on the honor system also. I haven't looked at the at what you wrote. Maybe I should have, because that would have given me a clue as to how good of a job I'm doing, or how bad of a job I'm doing in terms of presenting the material. But I'll leave that up to you to decide at some point. So what we'll do is go over the questions, and I'll try to answer them as best as I can. I think I'll make up the answers as I review the questions. So I'm not sure how this is going to go, but I guess I need one of these probably. So there were quite a few questions as I looked at this, devoted to the very beginning of our experience together, and I guess that's just the way it turned out. So, can anybody, let me do this. I'll ask for answers from you before I embark on an answer myself, if I need to. So, number one has to do with kind of a standard for video. And anybody know the answer to number one? How many lines does an old-fashioned TV set write on a screen? Anybody? Blurt it out. Yeah, that's it. 15,750 a second. 525 lines per image, 262 and a half for each half of it. And so that's a 525 and a 30th of a second, 262 and a half and a 60th. So then the next question has to do with the turntable test, calibration test. How many degrees per second does a 33 RPM turntable? 200. Very good. You know, I actually shared this with the internet, and some people answered this. And somebody said, well, it does 199.9999. Well, since that person was so specific, I would probably have to judge him wrong, right? I mean, the difference isn't very great, but why would I judge him wrong? It's because a third is an absolute number. You know, it's not point something something to infinity, okay? So a third means a third, and if you then multiply that times, 6, you end up with 200. Exactly. But you use a calculator. That's the problem. So the next has to do with focal plane shutter operation. And in this case we say that we have a slit in here, which, what is it, 1,000th of a second? Okay. The opening measures 2 millimeters at 1/1000th of a second. And the question is, how wide will that slit be at a 250th? Anybody? 8 millimeters, yeah. 4 times as big, right? Because the 250th is 4 times as big as 1,000th. Exposure time in a focal plane shutter is defined which way? Anybody? What?
Slit width over slit velocity.
Yep. Slit width divided by the velocity of the slit is equal to exposure time. Right, so, I mean, as you look at this, you kind of get the gist of how a focal plane shutter works. You have the slot moving across the focal plane, and the rate at which that moves, plus the width of the slit, determines what the exposure time is. So the next one had to do with a little test that we did with the LED, flashing LED. So how do you determine what the flashing rate of a flashing light is if all you have is a camera? Anybody? Nobody? Blurt it out.
You do the same test that we do with the LED, like we can pan the camera and see how many dots it makes in a second, or...
Okay, and there's one more thing that you need to know.
For each second you'll see 100 flashes. Number
That
of
was
flashes.
for-
Yeah, it was for the LED, but this is an unknown. It's like one of these.
Divided by the shutter speed.
Ah, right. You need to know what the exposure time was, right? And then you count the number of individual images that you have. Yep. Now there would be, if you had more sophisticated equipment, there would be other ways to do it. But a camera is a good start, or a camera that has a calibrated shutter in it already is a good start. So how do you describe the velocity of a moving subject, which is question number 6. And this was very nice. It was the exposure time. Well, suppose that you wanted to now determine what the velocity of something was.
Distance divided by time?
Yeah. Velocity equal change in distance divided by change in time. In fact, oh, that's right. It's not actually. It's not in here. Because that has to do with slit width. Okay.
What about the acceleration, the 2 times acceleration times the distance and square root of that?
2 times the acceleration.
Times the distance traveled and the square root of that whole thing.
Square root 2, acceleration, gravity, and distance.
Okay. So, velocity, right? And you're telling me that that is what?
The square root 2 times.
Square root of?
2AF. Acceleration of gravity and distance from that.
Divided by?
No, it's just nothing.
That's it?
Yeah.
Although this would tell you what the velocity of a subject is as it's falling from rest, okay, it is a special case, right? It has to do with gravity. It doesn't describe the velocity of a moving car. It doesn't describe the velocity of somebody walking from here to there. So, but, as I told Amanda, I'm not here to make your life painful. So if you chose this, mark yourself okay. So number 7 has to do with distortion due to focal plane shutters. And why does distortion appear in images made with focal plane shutter? Anybody answer?
If the subject is moving faster than the back edge of the curtain.
Won't give you that. It has, yes,
If the subject is moving in the opposite direction as the shutters.
I won't give you that either. Good try. Well, let's talk, okay? I mean, I don't want to be an adversary here. Just, my opinion is that would not do it.
Because the shutter increases in speed as it closes.
That wouldn't do it either. It has to do with the fact that as the slit moves across, you could have a subject, such as a tube like this, moving. And the moving image interacts with the moving slot of the focal plane shutter introducing distortion, focal plane shutter distortion. In this case, this bar, which is horizontal, would turn out to be like an inclined bar. So it's the interaction between a moving image and a moving slit that causes distortion. If the subject is standing still, then you can't tell the difference between a focal plane shutter and a leaf shutter.
So if you're, like I said, if the movement of the object is perpendicular to the movement of the shutter.
See, but actually it could be fine. But actually it could be, it doesn't have to be perpendicular. Because this bar, okay, instead of moving this way, could also move this way, could move that way, right? And now let's say that this bar happens to be moving at the same rate as that moving slit moves. And let's say a little further, that at some particular time, this bar and the slot are in the same place. Okay. And this relationship between the slot and the image exists here and also here. And also here. Okay, there's the slot. So what's the reproduction going to look like? Yeah, that's right. It'll be a blur that goes all the way across the frame, right? And if it doesn't go all the way across the frame, it means that either the image passed the slot or the slot passed the image, one or the other. So what you get is focal plane shutter distortion, and I think there's a question about this later on. So if you figure it came close, it's okay. So number 8 has to do with if you want to determine the speed at which something is moving, it can't extend, the blur can't extend beyond the edges of the frame. And the answer to that question is what? Anybody?
You don't know where to start measuring from?
Yeah. Or stop. Either way. Right, you need to know where the beginning is and where the end is. And if it's outside of the frame, you don't know. So number 9 has to do with a moving object becomes its own shutter in a manner of speaking. Well, what is that manner of speaking? How can a moving object become its own shutter? This has to do with the turntable test, remember? And we had the mark on the turntable and it's moving around. And so here's the turntable, here's the mark. If you make an exposure with this standing still, in that case this mark is in the same place all the time, if it's standing still. But if it moves, the energy, all the energy which is here, could be spread out over that much area, and all of a sudden that mark is not as bright or doesn't cause as much of an exposure anywhere as if it were standing still. So once the object has moved, or the image has moved away from some location, it no longer causes that location to receive any further light. So it means exposure has stopped for that moving object. Now exposure could continue because you could have an exposure of a year, okay, or a minute or whatever. But if the object is no longer there, it's not going to record. So we typically assume that objects don't move, that remain in the same spot and produce energy in the same area of the film all the time. Sometimes you can see this, maybe not exactly that same way. I'm thinking about Roadrunner cartoons. When the Roadrunner is running, okay, you just see this blur going by. If it's standing still, you can see it right there. So that's something to keep in mind. What's number 10? Wow, there's awful lot of words there. You make an exposure 100th of a second. With some camera with a 50 millimeter lens, I don't think that matters. But you make it of a 1 foot square object. Now this is what you know about the original subject. is that it is a 1 foot square object to begin with. So the image is also going to be 1 square something, 1 inch on either side, or a millimeter, it doesn't matter. But if the original is a square, the image is a square. So now you make a photograph a hundredth of a second, and in the final record, it appears as an image which looks like this, which has an aspect ratio of 2 to 1 instead of 1 to 1. And from this, you can deduce that the object moved how far?
2 feet.
Well, good. We have an argument. It moved 2 feet or it moved 1 foot. Okay. So let's see who wins. How far did it move? You agree it moved 1 foot? And this has to do again with the, to some extent, it has to do with the turntable test. Remember? In that case, we had the mark over here, and we had the mark over here, and we said, okay, you're going to measure from the beginning to the beginning, or from the end to the end. Okay. Same thing. Here to here. 1 foot, because originally this was 1 foot. This is 1 foot. So during a 1/100th of a second exposure time, it moved 1 foot, and so the speed was, what, 100 feet per second, right? Okay. Henry Lartigue, I think this is one of the images that I showed, exploited focal plane shutter distortion. Well, I don't think he did it on purpose. A lot of photographs happen by accident, and I'm sure that one was an accident. But what was the subject of the photograph? A race car. Okay, now we can go back, I think, for question number 12. We can go back to the original equation that we had here. And reminds us of what? Newton, right? Objects appear to pick up speed, why?
Because they're accelerating with the rate of the flow of gravity.
Because of gravity, right? As long as you had the word gravity in there. So, how far does the subject, question number 13, that's moving at 1,000 feet per second, move during an exposure time of 100th of a second? Anybody help me on that? 10 feet. So here we have this seed. And it's a test that you did. Except that here it's already marked up. Okay, you have to determine, you're asked to determine what the rotation rate of this seed is. To some extent now it depends on how precise you're going to be in terms of measurement of this particular figure. If you look at this, it has 1, 2, or 5 spikes to the left, right? 1, 2, 3, 4, 5. Correct? Okay. This, however, is time equals 0. That's where you start counting. I mean, that is your reference mark. So between this one and this one, it makes 1 turn. Between here and here, it makes another turn. This is the 3rd turn, and this is the 4th turn. Right? And your exposure time is 1/4 of a second. So the rotation rate is, in 1/4 of a second, it makes 4 turns.
Would it be 4.5 turns?
I'll buy 4.5. You could argue there is a little bit left here. Okay? So 16 or what? 18. Okay, 20 would indicate that you counted from here. You said 5, and that would not be quite right. And I hope you agree that that's the case, right? I mean, I'm not. So then you're asked on question number 15, how fast is the seed falling? Now you had a scale right next to that seed. It said, you know, this distance is 5 inches. Now in this case, okay, you can actually measure from the very top of the blur to the very bottom of it. And how far is that? How many? It's too hard for me to do this. Okay, I guess I'll do it. Start from there, end over here. 1, 2, 3, 4, 5, 6. 6.5. 5/8. Yeah, okay. In a quarter of a second, right? So we're talking, what, 24 inches per second? Or 26 inches per second? Is that right? 6.5 times 4? Is that 26?
Yes.
I don't have a calculator.
If you did 7 inches, it came out to the 28, is that exactly?
Oh, go ahead with 7. Okay, 20, 24, 26, or 28, depending on what distance you measure.
I did it, probably really stupidly, but I measured the distance it took to do one rotation, and then I said that there were 18 rotations per second, so I just multiplied that 1.5 inches for one rotation times 18. Would that be the same kind of thing?
Well, what did you come up with as a result?
27 inches.
That's in between here. I guess that works. Sure, that would be a way to do it. Okay. What's the decimal for a millionth of a second? 5 zeros and a 1. So, number 17, question is, when you measure the rotation rate of a subject, the measurement is independent of image magnification. What I guess this question is related to is when you're trying to determine distance that an object moves from a photograph. In that case, magnification needs to be taken into account. But when you're measuring rotation rate, in that case, magnification is independent or dependent? Independent, right. Because you can see whether something is turning, whether it's small or whether it's big. Okay? Makes no difference. So now you have a subject moving 100 feet per second, and it appears blurred in an image made with at a thousandth of a second. That's the top speed of the camera. And then you say, okay, well, how can I make the picture sharper? You know? And you decide to use a shorter focal length lens. So is the image going to be sharper or not? Yeah. The answer is that it will not be sharper. It'll just be smaller. Because and I was discussing this with a guy in Australia, and finally he relented and said, yeah, I agree. If you have a subject, and it kind of goes back to that object that moved a foot, okay, remember during some exposure time? So you have this subject here, and in fact, let's make it move a foot, okay? So, now it ends up to be twice as long as it's tall. And we know that it's supposed to be a square, okay? So we have a lot of blur. We say, okay, we'll make the blur smaller by using a shorter focal length lens, or moving the camera away, right? So what happens? Well, now we're going to have a subject, a reproduction which is this big. The ratio, okay, of this to this is the same as from here to here. Hasn't changed. It's just smaller. So you say, well, this is sharper than that. Well, I'll dispute that. Because if I take this, and through some magical means, it used to be that we could use something like that over there, an enlarger, which you probably don't know what it is. That optical device sitting on the table that takes a photographic negative and you blow it up, whatever blow up means. From the film era. But now you can do it by scanning and stuff, right? It's the same thing. You enlarge it. So that this becomes as big as this. It's going to be just as blurry. Right? So you really haven't gained anything. You just had, and in fact, you have lost a lot by doing this, because now you have to blow it up, and you introduce artifacts associated with enlargements. Often it's not a good thing. So you might as well just shoot at the largest possible magnification, because you're not gaining anything by making it smaller. At least that's my opinion. And I think in the slide presentation, I mentioned that some authors neglect to tell you that you need to make an allowance for the fact that you're going to enlarge a reproduction or not enlarge it. So anyway, oh my goodness, number 19 has to do with electronic flash. And some electrical engineer tried to get on my case. And I said, no, let's keep it simple, because this is not about an electronics course. So, but power, essentially watt seconds, were described or could be explained or quantified. I'm not sure that there's this in here. Yeah, it is the capacitance, the volume, okay, that you can, electricity that you can hold, times the voltage squared all over 2. This little relationship just says to you that if you want to increase power, what you want to do is increase voltage. Because increasing voltage, doubling it, quadruples the power, right? Because it's a squared factor. But the problem that you have in raising voltage is that eventually it becomes unstable and dangerous. So the practical limits to which you can raise voltage. And once you have reached those, the only way to increase power is to increase capacitance. But increasing capacitance has a bad effect on duration. So it's a trade-off. 20. Any questions on this? Okay. In order for an image to appear imperceptibly blurred, and the operating factor here is that word, imperceptibly, means not detectable. The degree of blurring must not be any larger than what? Anybody? The diameter of the circle of confusion.
Could we have said 10% of the subject size?
Ah, sure. Well, we can go with that. Oh, no, we can't go with that. See, because 10% of the subject size, you can't do that. I just thought about that. The reason that you can't do that is because the word imperceptibly is in the question. And imperceptible means that you cannot detect it. And the only way that you cannot detect it is if it's smaller than a circle of confusion. 10% of the subject size is an allowable blur, if you can't get really short exposures, right? And it says, 10% blur. Oh yeah, I'll notice it. Okay, I'll notice it, but I can live with it because I can't afford to go any smaller. So, the next question is another historical figure here. And it has to do with Harold Edgerton. And who was Harold Edgerton? Briefly. Anybody? Yeah.
He's the guy that made the electric flash popular, and he also wrote that little book.
And he also wrote that book. Yeah, sure. But the important part is that, he made the electronic flash a popular device. And he characterized it and explained it. And now we're surrounded by flashing lights all over the place, right? You get them at the airports, you get them in space, you get them. We're surrounded by flashing lights. So what's the approximate speed of sound? About 1,000 feet a second. If you said 1,100, that's okay too. So now the next question has to do again with electronic flash. And I'll just the words I think are enough. If you disconnect the main capacitor, so the source of energy from the flash tube during the time that the flash tube is being discharged, what happens to the duration and to the light output? Any takers on this?
The flash power will diminish and the output will decrease in intensity.
You give me the same answer twice. And the output will do what?
Decrease in intensity.
And what's the first part of your answer?
The duration will diminish.
Yes. The duration will diminish and the output will also diminish, right? Right. You have less light for a short time. However you put it, okay? The duration drops and the output also drops. So the next question, 24, actually has to do with something I mentioned a little while ago when we were looking at the equation, right? 1 second is equal to capacitance times voltage squared divided by 2. So if you double the voltage, question has to do with, well, what happens if you double the voltage? This squared, you quadruple the power.
What if you wrote write or flash?
Nope. Because that is a descriptive word. It doesn't tell you anything about doubling. Doubling is the operating word. But if you want to mark yourself right, that's okay. But realize that the question, the important part of that question has to do with doubling.
Did you say it increases the power exponentially?
It's just about as close as the other one. If you said 4 times or something like that, that would be more accurate than exponentially. Although it is an exponential factor, the fact is that you were given doubling. And well, just see how lenient you want to be with yourself. So, moving a sound synchronizer microphone a foot away from a source of sound adds how much delay to the next photograph? Anybody? 1,000th of a second. Yeah, because we know that sound moves roughly at 1,000 feet a second. So for every for every foot, we're delaying things by 1,000th of a second. So then number 26 has to do with the limits between which the duration of electronic flash is determined. So we want to take a look at the output of an electronic flash then. And it goes like this, very quick rise time, and then it has a decay time. Right? So the question is, where do we measure the duration? Well, we can measure it from the time that we see the first photon until we see the last one. Okay. But that is not the usual time that is given by manufacturers or that these are measured. Half peak to half peak. So you got a 50% output. It's as much of, essentially this is a one-stop difference from here to here, one stop. Right? And you measure from here to here. That's your change in time. From 50% output to 50% output on the downside, or half peak to half peak. The strange thing about this is that you're assuming that anything which is underexposed by more than a stop doesn't record a useful image, which is not the case. Right? So number 27 has to do with this very curve. So why the highlight blur looks like it does on the photograph. Anybody want to put it in words?
The bullet continues to travel as the light diminishes from one half stop to another.
Yeah, do that. Yeah, as the light keeps going down, okay, the highlights are the ones that are going to disappear last because they're reflecting a lot of light. The shadows are going to disappear quickly, and besides, at the very beginning of the flash, the rise time is very quick. But after that, it just decays slowly. As the light dims, the highlights are getting dimmer and dimmer and dimmer, while the bullet is moving further and further forward. And that causes the highlight blur to appear in the direction that the object is traveling. Okay, so what's an intervalometer?
Measures interval of time.
Sure.
It's a circuit.
A what?
A circuit
A circuit?
that turns a switch on or off in time interval.
Yeah, a circuit that turns a switch on and off at
In a timed interval.
in a timed interval. Sure, that will work. Yeah, in fact, I mean, the kind of the Latin translation of this is an interval meter. However, an intervalometer is used typically in time-lapse applications to trigger a camera every so often. Right? So I think your answer is quite right. But I cannot dispute that it's an interval meter. But so is a watch. So how much time should elapse? Oh, wow. I kind of remember this. This is kind of a toughie. How much time should elapse between exposures in a time-lapse sequence if the event of interest lasts 12 hours and you make it last 20 seconds at a projection rate of 30 pictures per second? Oh, man. So, the first thing to do is to figure out how many total frames we have, right? So, 20 seconds, 30 pictures per second. 30 pictures per second, 20 seconds, and so we're talking about 600 frames, right? Or 600 pictures. So now we say, okay, we have to use up those 600 pictures in how much time? Well, 12 hours. How am I going to do this? 12 hours, let's see, there's 60 minutes per hour times 60 seconds per minute. Is that right? So this becomes
43200.
so that's 3600, and this is 36,000 by 10, and then times 2. And that is 72. I must have done something wrong here. 3, 4. Is that anywhere close? Wow, and I did it without a calculator. Okay, so this, now we're going to divide by 600, right? Oh, pretty good, because we get 2 zeros here, and we get 2 zeros here. We can get rid of them. And now we're going to take 432 and divide it by 6. 432 divided by 6. That's kind of tough. Well, let's see. 6 times 6. 6 times 7 is 42, right? Oh, that's pretty good. So it's 7, and then we have a 1 and a 2. That's, how about 72 seconds?
Yes.
All right. Okay. So now, given a playback rate of 30 pictures per second, what is the framing rate at a time magnification of 1/100th? Anybody have an answer to that? 0.3? Anybody agree or disagree with that? Agree 0.3? And how did you get that?
Time magnification equals the rate of recording over the rate of projection.
So you like the rate of recording is equal to
Okay, yeah,
33.
that'll do it. Number 31, to compress time by a factor of 10. What should time magnification be? 31, anybody?
0.1.
Yeah? That's the decimal way of saying it. What's the American way of saying it? A tenth, right. So, Muybridge. What did Mr. Muybridge do? Horses, right. He showed that horses at a gallop will leave the ground with all 4 hoofs at a time.
Who did the
Yep.
milk drop?
Edgerton. So the 3 most desirable characteristics of high-speed cameras are: resolution is one, sensitivity is another,
Recording speed?
and recording speed is the third. So 34, to achieve the highest recording rates with both film and digital cameras, manufacturers ultimately compromise on what? Ultimately, it's resolution, and they do it a variety of ways. Typically, by making the picture smaller. Oh, I had an argument about number 35 with a person out in the internet. A computer nerd. Well, no, he said, well, the digits don't kind of fit together. I said, keep it simple. So the answer is 1,000, right? 1,000 megabytes is 1 gigabyte.
And is it 1,024 bytes in a megabyte? That one thing.
But 1,024 what? See, the answer, the question is very clear. Whatever it is, it's 1 megabyte. Now, I think that his argument was, well, you can't have that. Because the way that numbers line up, you just can't have that. But I'm saying, let's say you have a basket that holds 10 apples. And I have 1 apple. How many can I fit into the basket? 10. Right? Yeah, right. So that's the way to keep it simple. So number 36, had to do with a very small portion of the slide presentation about the rotating prism high-speed cameras. And I guess I included it because even though high-speed motion picture cameras are not used that much anymore, it's still kind of a talking point to remember those. And it's the thing that made them possible. And number 36 then, this rotating prism camera has a lens, has moving film, and because the film is moving, the image that the lens produces needs to be moved also. And that's done by putting a spinning mirror here, or a spinning prism, which, when it's oriented this way, takes the light-forming rays and sends them upward, and then when it's turned the other way, it sends them downward. And you adjust the speed at which this is turning so that the image moves at approximately the same rate as the film moves. That overcomes the limitation of intermittent motion, where you have to advance and stop, and so on. This way, just continue moving, and you can go much faster. So I think we're at 37, is that right? How do high-speed cameras, digital cameras, allow you to look back in time with reference to some event that you photographed? How do they do that? See, film cameras can't do that. And they can't do that because the medium is expendable. That means once you have exposed it, you can't use it again. But digital media is not like that. You can reuse it, right? So they do it. Every one of you in your film, in your high-speed films, videos that you did this. Okay. What they have is a number of frames that can be stored on the in a buffer, whatever that is. So what the camera does is you say, okay, start recording. So it fills up all of the memory that it has available, and then it says, okay, now what do I do? Normally it would just stop recording. That's what film cameras would do. But what this can do is it says, well, after I've done this, stored that one, I'll go back to the very beginning one, okay, and replace it. So this now becomes a new picture. Okay, and then this one becomes a new picture. And then this one, and then this one, and you continue going until you get to here. Once you're here, you go back to the beginning. So you're continuously recording. And all the time you're storing that many pictures. But it just so happens that at some point or another you say, hey, the event happened. And it happened right here. So you trigger the camera, say, stop recording. Well, the camera doesn't stop recording immediately because you can tell it when or how much longer beyond that point you want it to record. So what it does, it keeps recording, let's say, up to here. And then it stops. So this is what happens after the event has happened. But you have this and this remaining. So you can say, okay, well, I'll start playing back these images right here. And now you're in the past in relationship to that event. So you're looking at what happens before, then you see the event, then you see what happened after. Very powerful, and only possible with digital. The film people try to do this, but of course they can't. Oh, number 38. I remember this one. You could do this the easy way, or you could do it the hard way. See, the hard way would be to say, oh, he mentioned this thing about foot candles and so on. And I remember that equation. It was something to the effect that foot candles is equal to 25 times the F number squared, divided by exposure time times ISO. Is that right? So in this case, what do we have? We have we're given this is 6,400. That's a given. F number is what we're trying to find out, right? So 100, and this the exposure time is 1,000. So if that's the case, then this becomes down here. This becomes a tenth. Is that right? So if that's a tenth, then the denominator here will be multiplying up here, right? And then we can get rid of this. And then we say that, well, 10 times 25, so it's 250 times F number squared. Oh, that's pretty cool, because now we want to have this by itself. So we take 6,400 divided by 250, that's F squared, F number squared. And this is a 5 here. Oh, and I don't know what that is. What is it? 25.6 is F squared, so square root of 25, F5. Okay. All right, now that's one way to approach this. And I had a dream about this one. Well, you don't have to do it that way.
I did the easy way, but I can't remember how.
I'm going to try to figure out what the other way of doing it, the way that you might have done it. Let me just leave that there. So, that's interesting. I guess I had a dream about this. So at 6,400,
That's the sunny day.
it's a sunny day, right? So we should be able to do this at F16 at 1/100th of a second, right?
1,000.
Or it's F16, no, at 100th,
Yeah.
because it has to be the reciprocal of the ISO speed, right? So this would give us a proper exposure with a sunny day. Okay, but it's F16 at 1/1000th of a second, right? It's what we want to do.
So you
Or no, what we want to do is we want to use an exposure time of 1,000th of a second. So this is what we don't know. F number, right? It's still 6,400. So it means that at 1,000th of a second, we need to use a larger aperture than we use at F16. So all we need to find out is how many stops, essentially, 1,000th is away from 100, right? So we say 100th is F16, 200th is F11, 400th is F8, right? An 800th is F5.6, right? And now we need to go the little extra bit to get to F5. So how do we do that? I think the way to do this is to do it using logs. And let's see how we do that. So if we have a log of 100 is 2, right? The log of 1,000 is 3, right? So the difference between the two is, the difference between the two is 1.0, right? And then we say, well, it is 0.3 per stop. Is that right? So divide by 0.3, ends up to be 3 1/3. 1, 2, 3 1/3. Right? So we open up 3 1/3 stops beyond F16. And so you say, well, how do I get to 5? I have no idea. Could I figure it out? I probably could figure it out. Do you want me to figure it out? I hope you don't say yes. Okay. But realize it could be done. All right? It could be done. We should be able to do that. Figure out why it's a 5. But I'm not going to do it. So fair enough. Now, you don't need to turn those in. Okay, you'll score yourself. And if you're working as a team, in that case, as long as one of you gets a higher score than whatever the syllabus said, and I forget what it was, look it up. In that case, you turn that in as a lab report. Good enough? All right. Yeah, it says, I have so many lab reports, and one of them is the exam.
Do you round up?
You can round up. Remember I said this is America, this is a country that operates by the honor system?
Towns, I can't